So sometimes companies will make, let's say, chocolates or something like that, like Hershey Kisses. You know, they look kind of like this. You could use a regression to find this line and revolve that. You'd get your Hershey Kiss, and you could find how much chocolate's in there. That's a solid figure with a solid middle. Everything is filled in with chocolate, and it's pretty easy to do. You just say pi times whatever formula this is squared from however long the Hershey Kiss is. That's not what this video is about. We've already done 2 videos about those. This video is more of what happens when a company makes a piece of chocolate, like the Easter bunnies that you see that are hollow in the center. So you think you're getting a solid Easter bunny, and then you bite into it and you see that you've been ripped off, and instead it's hollow. So let's say you have a graph like this, and there's another graph, and you rotate this graph about the x-axis. Like rotate this will be your solid portion, and you rotate the x-axis all the way around and around and around. You can see that you're going to have a hole all the way through the center, so you'll be able to look through this piece of chocolate, but there'll be an outside that's thicker. It's thicker here on the bottom or the end than it is on this end. This end would be really thin, but still, this would be a cylindrical shape, and this would just be a strange looking piece. But here's how you would do it. Okay, you have to think of this as, I'm going to do a bunch of discs again. So this would be my big radius, and this will be my little radius squared. So this is how you do it. You have to do the big one separate. So you find the volume as if this G was not even here, as if this was one big solid hunk of chocolate. And then you subtract off this piece, which is the hollow piece, which is the little radius, you know, from here to here. You subtract off this blue part, and what you're left with is just the red part that's up here, in here, revolved to make a solid figure. Kind of hard to picture, but just takes a creative mind. And so this one would be pi times the integral, let's say this is 10, 0 to 10 of f of x squared. See, f is the big radius from the axis to the outermost edge, minus pi times the integral from 0 to 10 of the little radius, which would be g of x squared. And you would just, whatever these formulas are, is what you would actually square and actually integrate, and that's how you would get your answer. So I'm going to do an example where it's tangible, like regular old functions. Okay, so let's say I have, this is a very crude negative x squared plus 4 and x squared plus 2, but let's say I have this kind of strange looking shape. I'm going to bound this volume to be the y-axis, and x equals 1 is where this intersection is, so I'm just going to think of it practically as ignoring the rest of this, just to make this easier to see. And I'm going to revolve this shape around the horizontal line y equals 2. Okay, so this is going to be kind of strange, but it's going to look kind of like this. It's going to be totally solid across, let's say this is the bottom of the shape. It's going to be totally solid across the bottom of the shape, because from here to here, the end of the top is the beginning of the bottom, then it keeps going. And then this figure will kind of have like a funnel or like a flower type shape at the top. Okay, so maybe this would look like a flower or something, but anyway, we're going to integrate from 0 to 1. And we're going to go big R squared minus little r squared. Okay, so big R. How far is it from the axis of revolution all the way out to the top. Well, this is x squared plus 2. From the x-axis all the way to here is x squared plus 2. So it's definitely not that long, because from here to here is 2. 1, 2. Sorry, this is negative x squared plus 4. What we're looking at up here. It's not from here to here, which is negative x squared plus 4. It's only from here to here. So that's negative x squared plus 2. See, it's the distance from the axis of revolution to the edge of the biggest radius, the farthest away radius. So this radius right here is negative x squared plus 4. Take away this part down here. And it's kind of similar to the very first day of this chapter. Area between two curves. Okay, little r is from the axis of revolution, which is here, to the small radius. So this is x squared plus 2, but then take away 2, because we got 2 units here. So this is just x squared. Squared. So little r is x squared. Okay, so you'll want to FOIL all this out. So negative x squared times negative x squared is positive x to the 4th minus 4x squared plus 4 minus x to the 4th. So this would be pi 0 to 1. These x to the 4ths are going to knock each other out. And so integrate this just like normal. So this would be negative 4/3 x cubed plus 4x from 0 to 1, which is pi times negative 4/3 plus 4 minus pi times 0. So negative 4/3 plus 4, 4 is 12/3, so negative 4th, this would be 8/3, so 8 pi over 3 is that volume, units cubed. So this is a pretty strange procedure, but either way, this is about the worst of any kind of problem you might encounter. So because it's a washer method and the axis of revolution has been moved, so you have to account for that 2 unit shift in every one of your radii. So